Hey guys, welcome to our next lesson. Today we are doing two lessons again, 4-2 day 1 and 4-2 day 2, but we'll go through it here quickly. In 4-2 day 1, we are going to be looking at exponential models, so we'll have a lot of different equations that we will be using. My first equation is going to be the doubling time equation, which, like the name says, it's going to be how long it takes for a population to double. So if we have 10 people, how long will it take for us now to have 20? So the letter A stands for the ending population. This notation is read as A sub 0 because the 0 is there as a little subscript. So A sub 0 represents the starting population. And that's why it has a 0 there, because usually when we start counting, we start at the number 0, correct? So A sub 0 represents the starting population. T represents the time that has passed. So T represents the total amount of time that has passed, and D represents the time it takes to double. So the directions will tell you it takes 10 years to double, 5 years to double, and that's what we're going to put in for D. The next equation that we're going to look at is the continuous growth rate. And this is just telling us how long it takes for a population to grow. And A equals the ending population. A sub 0 always represents the starting population. The letter K, so this letter K actually represents the rate. Okay, so we're using this letter K now to represent the rate. As we have been all chapter, remember that the rate always has to be written as a decimal. So turn those percentages into decimals, and then T represents the time that has passed. Notice that my continuous growth rate also involves the letter E, and remember that letter E can be found in our calculator by pressing the second button and then the division button. That's where we see E. My third and final equation that we will be using in this lesson is the half-life decay equation, and this is just the time it takes for half of something to disappear. So if you had 10 cookies, how long does it take for 5 of them to disappear? And so A is going to represent the ending amount. A sub 0, this notation, remember, always represents, no matter what equation we're with, A sub 0 always represents the starting amount. T represents the time that has passed. So if 10 years have passed, 20 years, 30 years, whatever that may be. And H represents the time it takes for half to disappear. So in essence, H is representing the half-life. What is the half-life of this item? How long does it take for half of it to disappear? And so here is the summary of my 3 formulas. Again, make sure that you have these as you're completing the homework. Otherwise, it will be very difficult for you to do so. On the quiz and the test, you will be given all of these formulas, but you have to know which one to use and how to use it. So here is our first example. Write an exponential equation describing the given population at any time t. If the initial population is 200 and the doubling time is 5 months, here is my key phrase. If there's a doubling time, that means I'm going to use the doubling formula, which is A equals A sub 0 times 2 to the t divided by d. So my equation is going to be A equals, the initial population is 200, so I'm going to put in 200 for A sub 0. Then I'm just going to put times 2. T, how much time has passed? I don't know. My directions specifically tell me at any time t, so I'm just going to leave t as is, and d represents the doubling time. I'm being told that the doubling time is 5 months. So I just put 5, and there we go. So there is my final answer to this number 5. All I do is set it up. I don't actually have to do any computation in my calculator. Let's go to my next example here, number 9. In number 9, we're again being asked to write an exponential equation describing the amount of radioactive material present at any time t. So the initial amount is 100 grams. The half-life is 6 hours. So that should be the key phrase for me to know that I'm going to be using my half-life decay formula, which is A equals A sub 0 times 1/2 to the t divided by h. So to set up my final answer, instead of A sub 0, my initial amount is 100, so I'm going to plug that in for A sub 0. Then I have 1/2. T is the amount of time that has passed, but again, my directions tell me specifically we don't know how much time has passed. So I'm just going to leave T. H represents the half-life, and notice they tell me the half-life is 6 hours, so I just put in the number 6, and there's my final answer. I have set up the equation to represent the situation they've given us. In my next example, homework number 13, we're looking at a word problem here. A $2 bet is doubled until a win occurs. If a loss occurs, then L equals 2 to the n dollars is lost on the nth bet. Graph the function for 1 is less than or equal to n, less than or equal to 10. So we are going to be replacing the letter n with x. So instead of n, we're going to be using x because that's a variable that our calculator can graph. So ny equals, in my calculator, I'm going to graph 2 to the x. And when I graph 2 to the x, I want to go to second graph because that's going to give me this table that I see here. Okay? And this table is so important because this table is going to give me the points to graph. Now, something that we do want to take a look at is look how high these numbers go. This is my y column, this is my x column. And notice here on my x column, I'm going to want to go from 1 to 10 because that's what the directions say. The directions say in between 1 and 10. So on my x-axis, I can just do my normal skip counting by ones, just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But on my y-axis, I don't want my scale to be ones because if my scale is ones, I'm never going to get to 1024. So I'm going to make my scale hundreds. So I'm going to have 100, 200, 300, 400, 500, I'll go to 600, 800, and then 1,000, okay? So notice that you can have different scales. On your X and on your Y, you're allowed to do that. So let's graph my first point, 1, 2, so it's gonna be way down here. Now I'm gonna go to my second point, 2, 4, again, still way down there, 3, 8, there we go, 4, 16, we're still all the way down here because my first line represents 100. So 16 is still nowhere near 100. Then I'm going to go to my next point, which is 532. I'm still way below that 100 mark. 664. Okay, now I'm creeping closer. 7, 128. Now I finally crossed that 100 mark. I go to 8, 256. And notice now I'm getting much larger, much faster. And that's why we call it exponential growth. You grow very quickly. Now I'm going to graph my next point, 9, 512. And so notice now I am all the way up here. And then my last point, 10, and then 1024. So 10 and then 1024 is going to be way up there. So now I connect my points. And I have graphed my curve for this bet. I've gone between 1 and 10, And there's my graph. So my last example here for this lesson, and then we'll move into our next lesson, is looking at population growth. So we have the doubling time for a fruit fly population is 2.4 days. If we start with 5 male and 5 female flies, how many flies should we expect to have in 1 week for part A and then 2 weeks for part B? Now, this key phrase, the doubling time at the beginning, this should be really standing out to us to tell us which equation to use. So since it's mentioning doubling time, that means I'm going to be using my doubling time equation, which is A equals A sub 0 times 2 to the power of t divided by d. Now I'm going to split my screen in half because I'm going to have one equation for part A, one equation for part B. So for part A, I'm going to set this up as A sub 0, my initial amount. What are we starting with? We're starting with 5 male and 5 female flies. So what is that total? The total is 10. So for A sub 0, I'm going to put 10. Then I'm going to multiply by 2. T represents the time that has passed. I'm being told that 1 week has passed. But we'll come back to that in a moment. I'm going to leave T blank for now because I want to focus on D. D is the time that it takes for this population to double. And what does my problem say? The doubling time is 2.4 days. So for D, I'm going to put my doubling time of 2.4 days. Here's where the T gets tricky. 1 week is what should go here. But I cannot just write the number 1 because my units have to be the same. So if my T is in weeks and my D is in days, that is not good. So if 2.4, if my doubling time is in days, I also have to turn my week into days. And so how many days are in a week? 7. So that is what I would put here for the time that has passed. And there's my equation, 10 times 2 to the power of 7 divided by 2.4. And if I enter this into the calculator, I end up with an ending amount of 76 flies. So after 1 week, I would have 76 flies. Now let's go to part B, which is telling me after 2 weeks. So let's set up my equation. A equals A sub 0 is still going to be 10 because I'm still starting with 10 flies. I'm multiplying by 2. How much time has passed? 2 weeks have passed. But remember, I want to keep the same units. So 2 weeks is really 14 days because the doubling time is 2.4 days. So you want to make sure you keep those units the same. Now we can go ahead and enter this into the calculator. And after 2 weeks, I end up with 570 flies. And notice how quickly that grew. I went from 10 flies to 76 flies in a week and 570 flies in 2 weeks. And that's the whole idea behind exponential equations, that it grows very, very quickly. Now let's look at day 2. We're just going to add one new equation and then we'll do our sample problems. So the new equation that we have now is the relative decay rate. And this is just how long it takes for a population to decay or decrease. Decay just means that we're going down. So A is the ending population. A sub 0, as always, is the starting population. K is the rate. Make sure we write that as a decimal. And notice what's the only difference in this equation from the growth one is that my K is negative. Because since I'm decaying now, it's a negative rate. T represents the time that has passed. Okay, so this is the new equation that we're going to be looking at. Again, here's my summary of formulas, including the 3 that we did in the last lesson, and then just adding my relative decay. So let's go to my first homework problem, number 7. Write an exponential equation describing the given population at any time t. The initial population is 2,000. I have continuous growth at 2% per year. So that should be the key word for you to know that we're going to be using the growth formula, which is a equals a sub 0 times e to the power of k times t. So for a sub 0, my initial population is 2,000. So I'm going to put in 2,000 there for a sub 0. My e stays e. K, remember, represents my rate. And what is the rate? It is growing at 2% per year. So to turn that into a decimal, I put my decimal place, I go 2 to the left, and I end up with 0.02. T represents the time that has passed. We don't know how much time has passed. The directions specifically tell us at any time t. So I just leave t there as my variable. And here at the bottom is my final answer. This satisfies the question of writing an equation. A equals 2,000 times e to the 0.02 t. Now let's look at number 11. Write an exponential equation describing the amount of radioactive material present at any time t. The initial amount is 4 kilograms. There is continuous decay at 12.4% per year. So again, that key word should be that there is continuous decay. So I'm going to be using my new continuous decay formula, which is a equals a sub 0 times e to the negative k times t. So let's go ahead and start filling this equation in. A sub 0 is my starting amount, and I start with 4. So instead of a sub 0, I'm going to put 4. Then I'm multiplying by e. K is my rate. So I'm decaying at 12.4% per year. To make that percent into a decimal, I move the decimal point to the left 2. So I'm going to have negative 0.124 as my rate. T represents the time that has passed. The directions tell me I don't know how much time has passed, so I just leave that as my variable t. And here at the bottom, I have my final answer. This would be the equation. My next example, homework number 19 from page 414 in the textbook. If a farmer uses 25 pounds of insecticide, assuming that its half-life is 12 years, how much will still be active after 5 years and after 20 years? So this phrase half-life should be a huge hint to us that we're going to be using the half-life equation. And the half-life equation is a equals a sub 0 times 1/2 to the t divided by h. So I'm going to split my screen in half because on the left, I'm going to be doing part A, and then on the right, I'm going to be answering part B. Okay, let's set up my equation. For part A equals a sub 0 is my initial value. How much insecticide are we starting with? We're starting with 25 pounds. So I'm going to put 25 times 1/2. T is the amount of time that has passed. In example A, the amount of time that has passed is 5 years. H is the half-life. And the directions, I'm told that the half-life is 12 years. So I'm just going to put 12 right there. And so when I put that into the calculator, 25 times 1/2 to the power of 5 over 12, I end up with A equals 18.7 pounds. And again, this makes sense because I am decaying. So if I start with 25 pounds, after 5 years, I still have 18.7 pounds. Now let's go over here to example B. Let's set up my equation. A sub 0, how much do I start with? I'm still starting with 25 pounds. 1/2 is just standard for the equation. T is how much time that has passed. In example B, I'm told that 20 years has passed. So I put 20. H represents my half-life. My half-life is still 12 years. So I go ahead, set up my equation, and when I enter that into the calculator, I end up with And when I enter that into the calculator, I end up with 7.87 pounds. And again, we want to look at our answer, see if that makes sense, and it does. If we're gradually decaying, after 5 years, I have 18.7 pounds. After 20 years, I have 7.87 pounds. Let's look at my last example, which is homework number 29 out of page 14 in your textbook. And we're looking here at the AIDS epidemic. There were an estimated 39.4 million people living with HIV in 2004. Assuming the number continues to increase at a relative growth rate of 3.2%, compounded continuously, estimate the number of people living with HIV in 2010 and 2015. So in this word problem, the key phrase for us should be relative growth rate. Because again, on the quiz and test, you will be given the formulas, but you have to know which one to use. So relative growth rate tells me that I'm going to be using my growth formula, which is A equals A sub 0 times E to the K times T. I'm going to split my screen here in half so that I can do part A on the left and part B over here on the right. So starting with part A, let's set up my equation. A equals, for A sub 0, what's my initial amount? My initial amount is 39.4. So we know that we're working in millions, but I can still leave it as 39.4. Then I'm going to do times E, that's just the letter E in our calculator, that constant. K represents the rate. And we're told in the problem that it's growing at a rate of 3.2%. To turn that into a decimal, I go 2 places to the left. So my rate is going to be 0.032. And in example A, how much time has passed? We're told in example A that it's 2010. So how much time has passed? If initially we were in 2004, that means 6 years have passed. So this is the equation that we would now enter into the calculator. And so when we enter that into the calculator, 39.4 times E to the power of 0.032 times 6, we end up with A equals 47.74 million people. And again, look at our answer here, which I've boxed at the bottom. It's definitely unfortunate because we don't want to see the amount of people with AIDS growing, but if it is growing at 3.2% and there was 39.4 million in 2004, it makes sense that there are now 47.74 million people with AIDS in 2010, or with HIV. So now let's go to example B. Let's set up that equation. A equals A sub 0. Again, my starting amount is 39.4. So I put 39.4 times E. My rate is still 3.2%. So writing that as a decimal is 0.032. The time that has passed. In example B, I'm in the year 2015. So if I started in 2004, how much time has passed? 11 years. So that is what I'm going to enter into my calculator, this equation right here. And so when I do that, I end up with A equals 56.02 million people. And again, you want to look at your answer to make sure it makes sense, and it does. We have grown from 39.4 million in 2004 to 47.74 million people in 2010, and then 56.02 million people in 2015. And that, guys, is our lesson for today. Here are your homework assignments. Notice for 4-2 day 1, we have these problems, right? Part A and B for 16 and 18. For 4-2 day 2, you have these first couple that are very easy. You just write an equation. And then the last couple is where you have the parts A and B. They're a little bit more intense. So make sure in Google Classroom, you go to the correct homework assignment and you submit those there before the due date. Thanks again, guys, for joining me for this lesson, and I will see you for the next one.